Hello. Thank you. So this is going to be about deep learning and how it relates to artificial intelligence and kind of state of the art. So I'm going to give an overview of deep learning. I'll talk about different ways where it applies, and then we'll talk about some places where it needs to be improved to do what we want it to do, and then I'll conclude. So we can look at AI through the lens of System 1 and System 2. So there was a book a few years back by Daniel Kahneman, Thinking Fast and Slow. And so System 1, two parts of the brain, System 1, System 2. System 1 is kind of the fast and parallel part of our brain. It's the subconscious, face recognition, speech understanding, running. System 2 is slow and serial. So it's the conscious part of our brain we use when we're doing a PowerPoint presentation. We can generally only think about one thing at a time. Sometimes we can't even talk. And then when AI first started, like in the 50s and 60s, they underestimated how hard it would be to implement System 1. They thought they could do computer vision easily. In fact, there's an old story about, I think my intellectual grandfather told a student to implement computer vision in a summer. And that was like 40 years ago. And then they thought what would be hard would be things like playing chess, the System 2, the things that are conscious to us, doing calculus. But it turns out they were wrong. AI systems, up till a few years ago, had been lacking. Our serial computers were too slow. We had a lack of training data. We didn't have the right algorithms. And our successes were in these systems, but it was only because these are the only things we could do. Our successes were like playing chess and search and planning and logic. But in the mid-2000s, this really started to change. And so we got new GPUs, video game processors. We had big data, and we had new algorithms. And this was kind of where neural networks became deep learning. We scaled up neural networks into these big deep learning machines that we see today. And this is going to be the focus of the talk. So I'll first give you just the basics of deep learning just for a few minutes. So it all starts out with a linear humble function called a perceptron. So you have a weight times an input, weight times another input, weight times another input. You sum them up, and you see if that sum is greater than a threshold. And if it is, then you output a 1, else you output a 0. So you could have a question like, should I buy this car? And you have, the important factors, the gas mileage, the horsepower, the number of cup holders. You weight them appropriately, and you get some sum. And if it's greater than a threshold, you buy, else you walk. So we take these perceptrons, and we put a nonlinearity on top of them. And when we do that, we call them a neuron, just to be kind of cool, right? And so we take a bunch of these neurons together, and we form them together, and this is what deep learning is. So we chain them together, and so we can write it out mathematically. This is your weights times your input value plus some balancing factor, so it all comes to 0 if you need it to. And then just as this little nonlinearity. There's a lot of nonlinearity functions. One is the sigmoid. You get some value between 0 and 1. And the nonlinearity, again, is because we're creating a deep neural network, and if we keep it all linear, it just collapses down to a linear function. But the nonlinearity makes sure you keep the power in there as you have all these layers. And the B just offsets the sigmoid, so the center's at 0. So here is a graphical description. You have weights coming in times the input, weight times the input, weight times the input, your nonlinearity, and there's your output. So this is the basic building block here. And so from here, we can go to our traditional 3-layer neural network. And so up till the early mid-2000s, this was the basic neural network. You had a top layer, which would be an output. Is this thing a cat or not a cat? Layer 2 is a hidden layer because it's neither the input nor the output. And you have the actual pixel values in here, or the number values, or whatever it is you care about, the number of cup holders, the gas mileage, what have you. And these were trained using supervised machine learning. So you had a whole bunch of inputs. Maybe there were images, and then you wanted to know, is it a face in the picture or not? Is it a cat or not? Or a traditional example is like a loan application. So a bank could have a whole bunch of loan applications. They know which people have defaulted in the past. They can use that as training data and punish the machine when it doesn't do a good job of predicting if this person in the past, where they already know the answer, if the machine made the incorrect prediction. And then you hope to learn if it worked in the past, it'll work in the future. So train a network, and this training is done with something called backpropagation. And so what backpropagation does is it helps you modify the weights. And I'll show you the weights now. They are right here. So what you have here is a Y for the output. X down here is the input, which in our car example is cup holders and such, but could be pixels in an image, could be anything. H is the number of hidden neurons you have here. N is the length of this vector X. And what you're learning with deep learning is you're actually learning the values of these things here. You have a matrix here, which is H times N. So for each of these guys, there's a link to all of the N inputs. And there's H of them. So you have a matrix of H by N. And then you have a W, 1 by H up here, because there's just one neuron at the top. So that's a vector. And then you have these B's that are just the bouncing things. And then the function looks like this. And this is still the basic neural network. You have these two nonlinearities, and you have your W. And so what you're doing here is you're using backpropagation to learn the values of all these weights such that the neurons give the right output at the top for what you care about. And another way to think of these matrices is you can call them tensors, where a tensor is a matrix that can have arbitrary dimensions. I think mathematically it has some other properties that we don't use here, but you can call them tensors, and that's why Google's deep learning toolbox is called TensorFlow, because you have all these tensors, and what you care about is the numbers of these tensors. And so when you're doing deep learning, all you're really doing is updating the value of these tensors so you get the output you want. Now it's deep because there's a whole bunch of them. It's more than the 3 layers now. We've got many, many layers, and so these networks typically have millions of parameters. Hundreds of millions of parameters is common. And so to do backpropagation, what you're trying to do is you have some error function at the top. If you're trying to predict cats, you say, did this thing out, if it's a cat, what's the probability of this thing is it thinks it's a cat? And the difference between what it is and the probability it says is the error. And vice versa. If there's not a cat, the probability that says is a cat is the error. And you want to update each of these weights, all million or so, all 100 million weights, such that it's more likely the next time to correctly predict a cat. And the way that's done is through backpropagation. And backpropagation is like dynamic programming. So you have some error up here, and you're looking at the derivative of the error with respect to each of these million or so weights. And there's many ways that each of these weights can snake through the network in order to get the output. So backpropagation is like a combination of dynamic programming, which builds up the answer from the bottom, and the chain rule in calculus, which says the derivative of this is the derivative of this times the derivative of this times the derivative of this, and you can just multiply them through. In fact, Edward Zhang quoted as saying, the chain rule plus dynamic programming is neural networks. And so I mentioned TensorFlow. That's the Google toolbox, and Theano is another one, not Google, more of an academic thing. And what they do, the beauty of what they do, is they calculate these derivatives for you. So all you have to do is set up your network layout, say what your error function is, put in your data, and it computes all the derivatives and all that stuff for you. So that's real nice. Now, the difficult part is it's really hard to debug with TensorFlow. I gave a tutorial on TensorFlow a couple months ago, and I'll probably give one in the future, where we kind of go through how to set all that stuff up. Yes?
How do you know how many layers to do?
Yeah, well, so one rule of thumb is you make, someone else said this, I don't remember who, but you make it as big as will fit in your GPU memory. And then you add regularization, which is a penalty for having high values on these weights. And then that's as big as you make it. And so you try to overfit the data. So you have some training data, and you say, OK, I want to make sure I can perfectly predict this training data. And you keep making it bigger and bigger until you can do that. And then a lot of this just comes from normal stuff. So what you do as a practitioner, what I do is whenever I have a problem, I go out on the internet and find the closest thing to what I need to do, and I copy their solution, and then I tweak it until it works. Yeah.
You ever scale back after you've done it instead I have too many and now I can...
Yeah, because if it's too big, it'll overfit to your training data. So you don't, if it's overfitting on your training data, so doing really well on your training data, but not doing well on data it hasn't seen before, that might mean it's too big. So you have to scale back. Yep. Yeah.
You mentioned cats. How abstract can it be? I mean, could you have like pictures of cats, and then you had a big enough deep learning model where if you had a cartoon cat, it would recognize it, or does it have to be close to what your data set?
It has to be close to your data. But it's getting really good. In fact, we'll see some more machine learning vision later, so we can see a little bit how that works. Okay, so that's the introduction. So next I'll talk about natural language processing, then computer vision, then robots, and then we'll talk about what deep learning still can't do, practical ways you guys can get started. Then I'll conclude, and if we have time, I'll tell you a little bit about my startup, Deep Grammar. Okay? So, natural language processing. So, traditionally this has been done with symbols. You have a sentence, I bought a car, and you assign a symbol to each of these things. I bought a car, and you assign some meaning to each of these symbols, and that's the meaning of whatever it is, and that's the meaning of how the computer sees it. So, but when you do bought, you can say what happens with bought, but then you have to remember, okay, purchased. Right? And then with car, you have to say, okay, now a synonym for car is automobile. I have to remember to write that down in my system, right? I have to code that up. And well, what about truck? Well, is truck the same as a car? Well, kinda, and you might have to code all your symbols up this manually. And so this is very brittle, as you can imagine. So deep learning comes to the rescue here, or I don't know if it's technically deep, but what we're doing here is neural network type learning. So is this a cat? Remember this? So we want to predict if it's a cat. We can do something else. Instead of predicting if it's just a cat, we can make a prediction over multiple outputs. So you could say, is it a house cat? Is it a lion? Is it a panther? Is it a bobcat? And what we're going to do is use a softmax. And what a softmax does is it takes all these outputs at the top and makes a probability distribution over them. Okay, so now that we've done that, we can look at how we might learn word vectors, which is vector representation of word instead of a symbol representation. So we have here, you have a sentence, the man ran fast. And what you do is you give it a vector for a vector for man, and a vector for ran, and you have it predict the next word with this model. And you have a probability for fast, a probability for slow, a probability for taco, and a probability for bobcat. And each of these vectors is actually in some huge matrix over here, which is the number of words in your vocabulary, typically around 50,000. And the length of each vector, which is usually around 300. And so when it's the comes up, you pull out the and bring its matrix up, or its vector up here. And man, you pull them out. And then you let the whole thing learn, but you also treat these word vectors as part of your parameter matrix, like we saw before, like the W. And that way, these guys get updated so that at the end of this process of learning to predict, you end up with vectors that have meaning, at least relative to the text that you trained on. So we have now a vector representation. Now here it's only 4 numbers long, but typically it's going to be about 300, usually around maybe 50 to 600 long or something. It's a fixed size, though. They're all the same size.
I have a question. What do those numbers represent?
Nobody knows. Yeah. So they're just numbers that represent stuff. So these numbers, when they come in as inputs to this thing, these numbers, when they come in, they're numbers such that if these numbers are such, it can make a prediction of what the next word is. That's all we know. Yes?
How is this different from text prediction?
Text prediction?
Yeah, just like in Google, you enter something in.
Oh, yeah, it's likely how they do it. So, well, long time ago when they first started that, it was probably n-gram based. And so for each pair of words, you have a probability distribution over the next word. And And that works really well, except it doesn't scale up very much, because if you have, like, if you go, okay, let's go back 4 pairs of words, then it's 50,000 to the 4 is how much space you need to store all those distributions. And so what this allows you to do is by combining vectors, you can get away from that explosion of the n-gram thing. Yes?
So I want to get back to the question of the vectors and the numbers. Like I understand nobody understands, that's fine. But there are somehow features, right? Features that you extracted from somewhere. How are these features like generated? Like how did we decide on the dimensionality of this vector?
Well, the dimensionality we decide up front just based on what we've heard it works.
Oh, so that's the topology.
Yeah. And usually about 300 is normal to start. If you use a smaller vector, you can train it faster because you have fewer parameters, but you may not be able to encode everything you want to encode. And so you just kind of play with it until you get the right length.
Where are they extracted from? Is it from also part of the training algorithm?
Yeah, no, the training algorithm is this. And at the very end, this matrix, remember, it lives over here, and you can just take this matrix out, and the word, bobcat's right here, and it has a 300-dimensional vector, and that vector was useful when it was placed into this model for predicting words around it. And so that's the meaning, quote unquote, of bobcat. Yes, yeah, sure.
Is the vector for each word, is that an output of this training or an input for the training?
Output. Input is random. You just throw in random numbers.
So if we feed in X sample, the output is that, and a setup which will predict the next word. So both these are outputs.
That's right. Yes?
Context like man, fat, skinny, legless, sleep. How do you add other features to each one of these concepts that you got?
Yeah, like an example would be like bank. Bank could mean riverbank. It could mean a bank at the store. And so if you have the word bank over here, it's going to have to encode both of those meanings. But one thing you can do is you can say, I want a bank for a noun and a bank for a verb. But there are other words that, have multiple senses, even in that sense. So what you can do is you can use like clustering of the words around it to create like word 1, word 2, and word 3, where they're all the same word, but they have different senses. There are ways you can do that. But this is very specific to the data you train on. So, for example, like glove vectors, one word vector output, one of their training is on Twitter, and it behaves very differently than training of like the classic word vec that came out of Google, which was trained on news articles. So we have our vector here. It's just 4 long, but remember it's really 300 long. And so if vectors have a similarity score, we can say a taco is similar to a burrito. So when the output here, you find that the vector for taco and burrito are similar because they're used in the same context. Whereas if you have a symbol can just be the same or not the same. There's no sense of how different they are. Remember the example earlier we gave of the difference between a car and a truck, right? We want to kind of represent that they're similar but not exactly the same, and this does that well. They've even found that they have some internal structure, even though we don't know what any particular value is. If you take the vector for Italy and subtract the vector for Rome, you get some vector output. And that vector is going to be very similar to the vector for France minus the vector for Paris. So somehow encoding capitalness. And same with king minus queen equals man minus woman. So it's somehow in this vector is encoding stuff. And in fact, these kind of analogies is one way to evaluate how good your word vectors are being learned. Because they give it like an analogy test you'd give to like a high school student. This is to this as this is to that. And they see how well it does. And if it does pretty well, then they say, okay, this is pretty good word embedding.
What if you're doing some sort of understanding, but those terms aren't used in the data set?
Yeah, it would be terrible.
It would be terrible.
Yeah.
Okay. So everything you do has to be in the data set.
That's right. Yes?
Has anyone tried to construct a systematic basis for the vector space based on this?
There is, maybe, I don't know. But I do know that there is work where you do like variational generative model type of thing. So instead of having some vector representation of something, you actually want to have meaningful statements about something. Like, is it in the past tense? Is it in the future tense? Is it, if it's an image, is it written with a thick pen or a thin pen? And there has been work where they're able to tease out some of these things. Yeah. So these vectors are kind of grounded in experience. Kind of. It's basically the words around it, but this isn't the physical experience in our world, and we'll see that how that's relevant in a little bit. And their meaning is relative to predictions. And if for a new data set, if you have a bunch of legal documents, you'd want to run your own, because you can download vectors off the internet, pre-trained, usually trained on news articles, or with Glove, they're trained on I think news articles or Twitter. But if you have some in-house specific documents, real estate or something, you'd want to have it learned on those documents. And this is as opposed to symbols, which are arbitrarily assigned, and the meaning is only relevant to other symbols. So that's encoding a word vector, a vector for a word. But how could we encode the meaning for an entire sentence? So the algorithm for doing that, not the algorithm, one algorithm for doing that, is you make a sentence vector. You make initially the sentence vector be the vector for the first word. Then for each subsequent word, you combine the vector of that word with the current sentence vector. And you just keep going, combining these things until the last sentence vector after the last word is done, and that's your sentence. That represents your sentence. So let's see that. And this can be implemented in a recurrent neural network, and we'll see that here. So you have the word the. And maybe you did word2vec already, and you've learned vector, and you have some vector for the word the. And you say, OK, H0, that's the vector for the word the. Then you take the vector for the word the, combine it with the vector for the word patient with a neural network, and get the vector H1. So this neural network sits right there where the arrows come into H1 and takes H0 and combines it with patient and gets some new vector of the same length. So if your vectors are length 300, this vector is still length 300. Okay? And you keep going until you reach some stop symbol. And that last vector, H3, is now your sentence vector. And so this RNN is like a hidden Markov model, but it doesn't have to make the Markov assumption. It can go back arbitrarily far. Of course, you can only fit, you have the same length vector, so you can only fit so much information in there. But it benefits from a vector representation. And in fact, we'll even see a way around that limitation of only fitting so much information in.
But when you change a word inside a sentence, it can dramatically change it, right? And wouldn't the combination, adding those together, be the same or something?
No, it's sequential. So yeah, so this H's actually represent kind of a state of the world. And so the state plus the word determines the new state. OK, so what can you do with this? Well, you can feed this into a classifier. So you can find sentences that are positive or negative. Did people like my product? Well, let me look at all the Twitter posts and run my classifier on it. You can also do machine translation. So you can unwind in the other direction. And these models where you unwind in the other direction are called sequence-to-sequence models, or neural machine translation, or encoder-decoder models. And we'll see an example of that. So we have our H3, which is actually the end of the last sentence. I think the patient fell. And so now we're decoding, and we have a new neural network here that learns to take H3 and map it to the Spanish word L. So we're taking the patient fell, and we're translated into Spanish. So the first word is L. And now we take the previous state plus the word just emitted and compute a new state. Then with that new state, we say, given this state, what's the best word to write? We write paciente, and we keep going all the way until we get a stop symbol. And so el paciente cayó. Now, it doesn't have to be the same length. In this case, I wrote it incorrectly. It should be el paciente se cayó. But it just keeps going, and this neural network has the same parameters at each junction. It's actually folding in on itself. But you have these vectors here. These parameters here. It just keeps going until it hits the stop symbol. And this is now a large part in how Google does its machine translation. You need a ton of data to train this stuff. And what they do is they have a bunch of documents in English, and then the same documents translated into French, and then they train it sentence by sentence. And then, you know, English, German, German, French. And of course, it doesn't work as well when you have two languages that don't have a lot of documents in the same, you know, translated documents. But as long as you have a lot of data, this is pretty good. And in fact, you can even take this further, because recall, we started here with just a vector, right? And so if you have a meaningful vector and you have a lot of training data, you can turn this vector into whatever you want, any kind of sequence. And so you can imagine you have a picture here, and then you use a convolutional neural network, which we'll see a convolutional neural network in a little bit. You get some vector out of it. This is my son after a birthday party, got all wet. You have some vector, and then you just run through the same thing. Take this as your H0, and then you just keep going. And as long as you have a lot of images that are annotated with an annotation, a description, then you can generate this through, and you get sad, wet kid. In fact, these guys did this, and they have a lot of great examples. It'll be like a guy sitting there with a guitar, and it'll say guy with a guitar, or to have like a person playing with a dog, and it'll say person playing with a dog. And they have some notable failures too that are funny. In fact, there was a Twitter account that tweeted out notable failures of this. But it's pretty amazing stuff. And I have this presentation, the previous version, on SlideShare. So if you go to my LinkedIn account, you can get the links, and you can look at all this stuff yourself. Okay. So I mentioned that as it goes along, these vectors are still only 300 long, or whatever length you chose. So as you're moving along, you have to remember more and more stuff in the same amount of space, right? And so that can be a problem. So this guy, Badanu, came up with this thing called attention. So when you're right here at H5 and you're trying to figure out what word you should emit, Kayo, it can not only look at H4 and paciente, but it can go back over the encoded sentence, and it can look at all of these states. And in fact, the network learns to take a weighted combination of these states, input it into H5, and make a decision based on that. And so that's called attention. And so these models are quite general, these sequence-to-sequence models. So in addition to machine translation, you can generate all kinds of things. You can do parses for sentences. As long as you have a lot of pairs of sequences, you'll be okay. In fact, you can even start to answer questions with all this kind of deep learning NLP stuff. So, you know, we've already answered one kind of question. What is the translation of this into French? Or what is the next word? And one thing we can think about is as it's doing attention here, it's looking at H0, H1, H2, and H3. You can think of it as looking at a set of previous facts to decide which fact is best useful for making this decision to output KO. So we can just generalize that idea to general questions. So H0, H1, H2, and H3 can be propositions or parts of a story or anything. And it can learn which pieces of the story are important for answering questions about that story. So let's look at an example. So we have a bunch of stories kind of like this. Bob went home. Tim went to the junkyard. Bob picked up the jar. Bob went to town. Where is the jar? The answer is town. So as long as we can generate a whole bunch of stories like this, these guys have been able to show that the computer can answer the questions. But you have to have a whole bunch of stories. And we'll see later that I don't think there's a lot of actual understanding going on here. But it's really fascinating stuff. Here's another example. The office is north of the yard. The bath is north of the office. The yard is west of the kitchen. How do you go from the office to the kitchen? And it'll output a sequence of directions. And so as long as you give it enough of these kinds of stories, for a new story of that kind that it hasn't seen before, it can output the correct answer. So that is introduction and natural language processing. Any questions so far? Cool. We'll go on to vision. Yeah.
Can you go back one slide?
Maybe I can't. There we are.
So, like, the two things that are important at the bottom structure that you have is noun and direction.
If you were to build something around this, would you leverage somebody else's? Is there algorithms out there that'll boil up like these are the nouns of the sentence and how they're related? Like the grammatical structure of the sentence is what I think people understand of the sentence, which makes it really easy for us. Is there that for deep learning and AI, or
There is some work.
is it just a whole bunch of just vector analysis?
This is just a whole bunch of vector analysis. There is some work where they parse the sentence first using traditional symbolic methods, and then kind of build up the parse tree. So instead of like a traditional parse, you have like a sentence goes a noun phrase and a verb phrase, and those things break out. And what they do is they put a neural network right here where these two things come together. So you have a vector that takes advantage of the noun of the symbolic knowledge built in.
Right.
But I don't think this uses that. And one disappointing thing about deep learning work is there hasn't been a really good integration between these symbolic and sub-symbolic methods. They're kind of in separate worlds. We haven't quite figured out a good way to integrate them. Okay. So computer vision is surprisingly hard. So the computer, this is obvious to us, a 5, but a computer just sees as vectors and numbers. And if you move, if you're looking at a chair or something, if you move just a little bit, the whole matrix changes. Because what you get is an RGB for each pixel value, right? Or even in black and white, 0 to 255. So if you move just a little bit or the light changes a little bit, the whole matrix changes. And that's why vision is so hard. So we need some kind of abstraction. And so in the mid-2000s, Hinton came up with this thing called what they had been around a while, but he put together this body of work around these stochastic binary neurons where you train them to kind of auto-encode themselves, and you limit connections to be from one layer to another, restricted Boltzmann machines. And you can build up layer by layer increasingly abstract representations, because what you need is abstraction, because if I move here, suddenly that chair completely changes. And it doesn't seem that way to us because our eyes do all this stuff subconsciously that we don't know about. So they kept building up, and then you train layer on layer, and they started to have some success with this deep neural networks in vision. In fact, this got scaled up by Lee et al., and they were able to take like low-level features and build up these levels, and the low-level features looks like things you see in the V1. You might see this in like a neuroscience textbook. You keep building up, and at the higher level, you get these like things that look like faces. This is really amazing because it's learned features that actually make sense. I started doing, in the early 2000s, I was doing face detection in computer vision, and at that time, that was a really hard problem. And to have something like this that just kind of learns these features from the bottom up, I mean, it's really impressive. Now, in fact, this was further scaled up by Kwok Lee et al. And what they did is they took thousands of computers and had them run on YouTube videos day and night, like I think a couple weeks or something. And it was able to find the most important thing on the internet. It was able to, by itself, learn cats. There was a neuron that fired whenever there's a cat in a picture. All by itself. It didn't have to tell it what cats were. It just was able to say, okay, this is what's important on the internet. And it learned by itself that cats are integral. And this is important because in order to have like a real understanding, a computer is going to need to learn about the world on its own, because we can never know all the features that are important. In our brains, all this stuff happens subconsciously, which is why we're so bad at seeing how hard it is. Yes?
So for the vision applications, is there a big difference between using restricted Boltzmann machines and typical neural networks, the sigmoid and regular?
Yeah, so since that time, since like the mid-2000s, they moved more to a convolutional neural network, and these are more supervised training. And those have done really well, and yeah, we'll talk about that. And that's what's popular now, these convolutional neural networks. So we saw unsupervised learning meanings of words, and we saw here with these deep Boltzmann machines, we learned features of the world through experience. So this is kind of neat because it gets our computers away from being so brittle. Okay, so now CNNs started coming on strong, and they could train many layers. And a CNN is a neural network that has these things called convolutional layers. So you have these feature detectors that kind of run over the image, and they register their highest point they found, and only that highest point, whatever feature they're running, gets reported up. So you have all these feature detectors running, and the computer learns the best feature detectors. So it used to be we used to put in feature detectors, like the Laplacian, but now it learns them all by itself. And you have all these feature detectors, and nobody knows what's going on, but the computer knows that this feature needs to be this way, and this way, and if these are all together in this way, then maybe there's a cat. And this is now how most vision is done these days, using different convolutional neural networks, which is cool because one of the things I really enjoy is watching our neural network architectures get increasingly complicated, and I like to pretend that we're getting closer to the brain, even though we don't really know how the brain works. But it's really exciting watching this happen. And so ImageNet is this huge corpus of images. And so in 2012, deep learning really jumped on the scene because they have a competition every year where they see, can you predict what's in this image, or can you say what's in this image? Is it a bird? Is it a chair? Is it a television? And in 2012, they used convolutional neural networks, and they destroyed the previous best. Usually, they're getting better just a tiny bit every year, but then in 2012, it just got a whole bunch better. And it's been, to a large degree, convolutional neural networks ever since then in computer vision. In fact, in 2015, they're able to surpass human ability on this task. Now, that has a big asterisk by it, because what they're able to do is they're able to pick out different breeds of dog. Like, I only know like 3 different kinds of dog, but this thing knows like 20 different kinds of dog, and it can pick out the particular breeds. But there is another asterisk here, is that you can take a trained deep learning system on vision. Let's say it learns to identify a school bus. And you can do this procedure where you change one pixel. And if it still says it's a school bus with the same confidence, you keep the pixel. And you just change another pixel randomly, and if it says, okay, that's a little less of a school bus, you leave it alone. You change it back to where it was. But you keep doing that until you find pixels you can change where the algorithm will still say it's a school bus. If you keep doing that process, you'll get to some white noise thing, and the algorithm says, yep, that's a school bus. So for a human, that would never happen to us. But you can still fool these neural networks. So you can tell that they're still very much data-driven. But they're getting a lot better. It's really amazing. OK, so that was computer vision. Now let's talk about robots. So when we think of doing things, we think of using the system 2 as we act in the world. Like, how am I going to get to Seattle? I need to book a flight, and I need to find my phone. I need to walk to the airport or call an Uber if I live somewhere other than Austin, right? But a lot of action is really a gradual stamping in, as Thorndike said in 1898. And this gradual stamping in of behavior was created as behaviorism in psychology, and that raged through psychology in the middle of the 20th century with Skinner and the Skinner box, and all they studied in psychology for the longest time, well, not all they studied, but a large part of what they studied in psychology for a long time was under what conditions would the rat press the lever, and how long would it press the lever, and how could you change the world such that it would press the lever a little less, all these kinds of reinforcement schedules. And this got encoded into computer science for robots in something called reinforcement learning. So reinforcement learning is a way to train your robot rat without telling it exactly what to do. You just give it a reward if it does something good, or you punish it if it does something bad. So you can see an example. So you have some pot of gold, which is a reward. Maybe the robot needs to learn to go to charge itself or get to some particular area. So the robot will wander around randomly until it gets to the pot of gold. And then it remembers how it got there. And so the pot of gold is a great state. But this state's right next to the pot of gold, so that's a pretty good state. And this state's right next to the state that's pretty good, so it's a pretty good state, and so on. And you have this, this function Q, which is a cumulative expected discounted reward of being in this state and taking that action. And so you learn this Q function. And so the hard thing about reinforcement learning is, how do you represent the state in a meaningful way, because of course this is a grid world, but our worlds are so vastly huge that you couldn't represent it in a grid, and if you tried to represent it in a grid after you got past a few variables, there would be so many states that you couldn't explore them all. And so, and this of course, if you explore a bunch, you learn the whole state. But as I was saying, as the world gets big, you just can't explore the whole thing. So you need some kind of abstraction on state. And as we've seen with deep learning is particularly good at that. And so what they did is they taught it how to play Atari using actual frames. So what you see when you watch the game, they fed it frames, and they had convolutional neural networks learn these states that it uses. And then on top of those convolutional neural networks states, they learn for each of those kind of states in that space, this abstracted space that it learns all by itself, they learn the value of moving each way, left, right, shooting, or reloading. And so doing that, it's able to play simple games where it doesn't have to look forward too far. So I think it plays like, what was the main one? Missile Command, not Missile Command, but the one where you shoot the dudes as they come down. Space Invaders. And now it plays a whole bunch. It first started off with Space Invaders, and now it can play a whole bunch. I think it still has trouble with games where you have to think really far ahead, because this is kind of, reinforcement learning is kind of this, this system one, right? It's kind of a state response kind of thing, right? Whereas if you have a plan ahead, that's not so strong for these kind of things. But it's really significant advance. Okay, so that's robot actions. Now let's talk about what deep learning still can't do. We've looked at system one, and we've seen that with computer vision, we're doing really well. Like our computers can now see in some ways almost as well as we can, and reinforcement learning is doing increasingly well. But it's kind of like when you get new carpet, suddenly your walls look ugly and you need to redo the walls. Our system two now is looking pretty silly. It still lacks common sense. You know, Siri, you talk to it and you're not talking to anything intelligent, right? It's not what it needs to be. I mean, Siri is very impressive, but not nearly as impressive as this vision stuff, right? And so Siri and this kind of, and Siri is a stand-in for common sense knowledge. We really need to move a lot in that direction. So we saw about how meaning can be encoded, especially with words, with the words around it, but there's no linking to the physical world. So maybe we need like this is a little iCub robot in Europe, and maybe it needs to, like, you hand it a cup and it says, cup. And cup means not only blue, of course, as it sees other cups, it'll see that it can be other than blue. Cup means having your hand like this. And cup also means if you go like this, water comes out. And cup also means if you drop it, it makes a noise. All those things go into the meaning of cup. And you're not going to get those things just by reading text. So like a word-to-vec thing we saw, you can't learn what a cup is. You might learn, there's been work where they say you can learn the affordances of words. So let's say the word cup. Affordance means something you can do with something. So an affordance for cup, all the affordances for cup are storing objects, pouring objects, drinking. And if it learns text, it can read like, by reading text, it can learn, okay, with a cup you can drink, you can spill, you can drop. But it doesn't know what any of these things mean because it's still only just text. Because it doesn't say, you know, words don't actually express when we read everything that we need to know. So the classic example is I talk about, you imagine reading a romance novel and you can say the boy looked into her eyes and pushed the table away between them. And as he did, all of the objects on the table moved with the table and they made a noise as they fell to the floor. You wouldn't say that because all of that is implied. And it's the same way here. In order to learn all of that stuff, you need to actually act in the physical world. Maybe. I don't know. That's one hypothesis. And so let's go back here. So these stories look pretty small compared to what we have to really understand about the world, right? Bob went home. He went to the junkyard. Where's the jar? It's in town. It just answers town. It just picked out a word out of this here that it thought would be the answer. But it doesn't really understand if the jar's in town, that it's not somewhere else, or that the jar could break if you drop it. It has a very limited understanding. Or in this example, imagine a dude standing on a table. So how would a computer know if you move the table, the dude also moves, right? I actually have an idea about that, and we can talk about it after they stop filming. So how would the computer know that you can move the table and the dude also moves? You would have to kind of experience that. Or how could a computer know that it only rains outside? Or as Marvin Minsey asked, how could a computer learn that you can pull a box with a string, but you can't push it? You're never going to see that written down anywhere, because no one's going to bother to write it down because it's so obvious. And so we could tell it all of these things, but there's just so many possible things to tell it, we could never tell it everything. It needs to be able to generalize from experience. So that is deep learning, natural language processing, computer vision, robotics. That's an overview of where we are in the field and the state of the art. We've talked about what deep learning still can't do. So that's kind of, you pretty much know the state of the art. We can talk about how you can get started in deep learning if you're interested. So there's a textbook available for purchase and free online. And you can read like, HTML snippets, but the whole thing's there. It's really well written, understandable, deeplearningbook.org. TensorFlow is Google's deep learning package. It's kind of the most common. And that's important because I told you how practitioners often do deep learning is you find someone who's done the most similar thing to you and build on it. And so you want to know the most common language, so that's where TensorFlow is good. And so they have a lot of tutorials about getting started. Google has actually done a course, an Udacity course that I believe is free that you can take. And then there is a organization, OpenAI, that they have a lot of clear explanations of some of the latest results. And so that's a good place to go. Okay, so to conclude, so system 2, slow and serial. Before deep learning came along, they could do calculus, they could play chess. This was kind of the state of the art. They could do planning. But now with deep learning, system 1 is really all of these things we've been reading about in AI advances in the last 5-10 years have been really these system 1 kind of things, perception kind of things. And as Andrew Ng, one of the giants in the field, says, pretty much anything that a normal person can do in less than a second, we can now automate with AI. So now we need to go back to system 2 and, in my opinion, get back to work on this and see how we can integrate these things. As someone asked before, how well is knowledge of the world integrated in deep learning, and we really don't have a good handle on how to do that yet. Yeah, and I think we may have 4 minutes. I can tell you about Deep Grammar. So Deep Grammar is a grammar checking company, and I make a lot of dumb mistakes when I write. Everybody does a little bit, but I make a lot of dumb mistakes. And I've always wanted a grammar checker that could fix these things. I mean, I know how to write more or less, but my hand just doesn't. And so this is surprisingly hard because it's particularly difficult to write an English grammar that covers everything. So you need kind of deep learning to learn the sequences of words, the common sequences of words. And the way this used to be done is people would use n-grams, like I mentioned before, literal sequences of words, and you look at, for this sequence of word, what's the probability distribution over these other words? And if someone wrote a word that's kind of not belongs there, has a low probability, well, maybe that's the wrong word. But this doesn't scale because you can't just store all these probabilities in memory. And so deep learning allows, with the abstraction, to finally do this. And we've very recently in Deep Grammar integrated symbolic methods into the system as well. And so now it works pretty well. So if you can try it online. We run it on a little itty bitty, we're self-funded. So we run on a little itty bitty Amazon computer. It's not even a GPU, so it's slow. But the concept is there. And
So you get the structure first, the symbolic, and then you use.
no, that's not how we do it. That would be one way to do it, but the problem with that is if the symbolic method is wrong,
Somebody writes the sentence wrong.
yeah, then the structure is going to be wrong, and then it just falls apart. Yes?
Does it do anything like, say for example, you have passages written very passively and you want to make it active, put it actively?
It does not do that. There is, that actually can be handled pretty well with rule-based systems. You can look for, because passive is like was verb, is blah, instead of this does. And so you can catch that with rule-based systems pretty well. But what's surprisingly hard is to catch stuff like a missing word, a missing article, or you meant to write one word and you write another word and they're both nouns, so it thinks it's fine. And that's where deep learning is really strong. Well, cool. I'm all done. Thanks. Yes.
In terms of the deep grammar program that you're working on, is it shipping yet, or is it still in development?
It's still in development. What we're looking for, so there is some giants in this area, like Grammarly is one. And what we're looking for, just as these three dudes, is some little niche that we can go into and really attack. And we haven't really settled on that niche just yet. Yes?
I like the concept of what I call Yoda speak, presenting a sentence that's totally scrambled out of order and having it figured out anyway. The second question, there's a famous piece by Isaac Asimov, The Three Laws of Robotics, that go into the ethics of robot behavior and how we use them. Are ethical weights or features in these multiple methods, is that just going to get in the way of artificial intelligence and NLP evolving, or should the ethical question be the last gate at the output?
Yeah, so that's a really big issue and a fascinating one. And one of the Nick Bostrom, I think, wrote a book where, thinking of reinforcement learning, right? He says, let's say in his example, you tell a robot you want it to build paper clips. It's a paperclip building robot is his example. And you think, well, what could go wrong, right? So you have it build paper clips, and it figures out, initially it figures out better ways to build paper clips, and maybe you can change this alloy a little bit. But let's say the thing gets really, really intelligent, right? It may decide that the best way to build paper clips is to shut down all human activity and just keep building paper clips. And this is, that they call the value function. And so how does the value function play in? And that's a really hard one. And we don't really know, because we don't really understand what our values are. In fact, there was a funny video from some news site a couple of months ago where they had a robot in a room, and the robot's like, well, can I just look at the most esteemed humans? Can I look to religious leaders to know how to act? And they're like, no. What about politicians? They seem to be your leaders. And they're like, no. So yeah, it's really hard to specify. And I worry most about job loss. So as robots, self-driving cars and get better and better, I fear that there's going to be fewer and fewer jobs for people without a lot of education. And some people have said, well, people have been talking about that for hundreds of years, and technology always makes more jobs than it destroys. But my fear is that computers are different because they're so general purpose. We don't know yet, but that's what I worry about. Yes?
So what's the state of the art in terms of evolution at this point, continuing research that's opening up better algorithms, methods, combining this with other?
Yeah, so one thing is called generative adversarial networks, which is real hot right now. So what you have is this machine that's learning to create like sentences or images, and it's learning a generative model, which means it's learning a model that allows it to create things. So you can take some abstract code and then have it create a picture of somebody. And then you have a discriminator, another neural network that tries to predict, is that image that this thing created, is that a real image or was it created by a computer? And so they get in an arms race, because as the discriminator gets better, the discriminator tells the generator if it did a good job of creating the image. And it gets better and better. And so now it can create all kinds of images. And then you can start to tease apart the meaning of this code, which for some reason lives right here. And you can say, okay, this indicator right here means the person has glasses. And this indicator right here means the person has dark hair. And then you can say, give me a picture of a blonde person. let me flip these bits, flip these switches to give the person glasses and give the person dark hair, and suddenly it'll convert this picture into that same person but with dark hair. And I think I saw that it can move like shoes to handbags. I mean, it's getting really cool, the stuff you can do with these generative adversarial networks. And that's the hot thing right now. Yes?
One of the challenges in applying this into the real world right now, for instance, deep learning for autonomous vehicles, is how much learning is necessary, to take into account various scenarios that are edge conditions.
Yeah. No, that's definitely the problem with autonomous vehicles. I mean, it can do 99.9% of the time just fine, but for driving, it has to work all the time. And nobody really knows how hard it's going to be to get that last little bit. Like a road closed and you got to go around, or there's like a traffic cop, all these things that it's not going to really know how to handle. And so one option is to have cars where the human can take over if necessary. But I think that won't work because I'm either driving or not driving. There is no I need to take over kind of a thing. And so that's kind of the state of the art now.
Well, there's also the concern that the government's putting rules in place that we need to demonstrate that the training is sufficient. How do you validate the deep learning training is sufficient?
Yeah, well, they have them training in Grand Theft Auto. Like, they'll actually train from Grand Theft Auto data. But as far as knowing for sure that they're always going to work, there is no way to know. You just have to field test them. I mean, I say all that, but I'm a big proponent of self-driving cars. I mean, we humans are terrible drivers. So I think a robot would do a lot better. Yes?
Neural networks is a metaphor for human brain nervous system. I always have a problem understanding what they are using out of a nervous system and considering the neural network. What are the features of a nervous system that are part of a neural network?
Oh, not much really. Yeah, I mean, I think we say that just because it sounds cool and is easy to understand, even if it's wrong. I mean, we don't really understand the human nervous system very well. But the only thing I think that really ties in, and there are some people who say that certain things tie in really well, like sleeping is a certain kind of update. And there's even something called the wake-sleep algorithm, where during sleep we generate samples and we train from them. But going way back, I think it just comes down to you have different relatively simple computations that feed into each other. I think that's about the extent of how we can say it's similar to the nervous system. Now, there are a lot of people that do really sophisticated modeling of neurons, and I think that sophisticated modeling is different from the stuff I've showed you today. Yes?
Can you summarize in the Austin area, like the state of deep learning, deep intelligence here, companies, and how active?
I think, so of course the big weight is in Silicon Valley. I don't know, there's not a lot of new research outside of UT that I know of. I mean, there's no, we don't have, I think we have Google here, but they're a very small office. You don't see a lot of papers coming out of the Austin office. Yeah, I don't know, I don't think it's really a hotbed or anything like that. So a lot, almost, not, I was going to say all, but all companies, not all, but a lot of companies now who use like data science and stuff, because of things like TensorFlow, they're able to run some amount of deep learning right out of the box and do it pretty easy. You can download some algorithms without even understanding how they work and run them through. And I think a lot of companies are looking at that, especially because deep learning does a great job with generalization. Yes?
Has deep learning ever been used in like optimization, like traveling salesmen or any of that stuff? Or?
I don't know about traveling salesmen. I'm sure people have tried it, but I know it was used, I think at Google, they used it to limit their electricity consumption in their data centers. In fact, I think they used the reinforcement learning algorithm that we saw to limit, not data consumption, electricity consumption. And I don't know what the decisions were, which switches to use or whatever, but they were able to limit electricity consumption. Yeah?
And going back to the
autonomous cars. These are the processes that you're talking about. They're doing unstructured learning. So if something malicious or just accidental happen and they fail, how do you fix them, or can they be fixed?
Yeah, no, it's funny because I've seen some articles where people talking about it'd be fun to hassle electronic cars, right? Like if someone's driving down the street, you don't want to walk in front of them because it's a human and no telling what that person's thinking. But electronic car is going to stop, you know. So you can people like walking in front of them and hassling them, and you could get like somebody was talking about, I forget his name, I'm sorry, but it's kind of robotic smog where you have a bunch of electronic cars and they kind of all waiting for the other one to go. Not electronic cars, but autonomous cars, waiting for each other to go, and they kind of get in a deadlock situation. Yeah, no, that's going to be hard. We don't really know how that's all going to play out.
So they could maliciously become weapons instead of vehicles.
Oh yeah. In fact, I read a book about a guy who was able to control like a fleet of autonomous cars to run people over, and but I think the deaths are going to go down compared to humans driving.
Essentially, we aren't at the step where we're the final step with this technology. We'll have to have structured systems that can be repaired should they fail, and be understood and diagnosed and dealt with, not the state that they're in right now where we have no control or no knowledge of the direction that they take.
I don't know. I think we have a ways to go before they're ready, but I don't think we have to do anything qualitatively different. I don't think we're ever going to be able to prove that they work. We're just going to start field testing them and see that they kill fewer people than human drivers, and then we'll say that's good.
But that's not taking into consideration a system, a program, alter a malicious program.
Yeah, like a hacker.
Or a failure, and we have no way of diagnosing nor giving a rule set to prevent it from doing that.
Yeah, so with deep neural networks, it's hard to understand why they're making certain decisions. Yeah, so you have to do a lot of testing. But I don't think we'll ever be able to prove, kind of like to do with cybersecurity. Some people try to prove that this system is secure under certain conditions. I don't think we're going to get there with cars. But I don't think we have to, because we're killing so many people every year. Yeah.
High schoolers out. There's no proof.
Yeah. In fact, in my town in Buda, someone was killed just this week. So, yes.
So I've heard a lot of articles about AlphaGo. The algorithm that solved the Go would be the world's best player.
Mm-hmm.
And it seems like it's really encroaching onto the type 2, the slow serial learning. Do you know like exactly how they did the reinforcement learning, or what was so special about that?
I think they used the algorithm I just showed you for playing Atari. Now it was modified, and they added, I think, search trees. I don't know exactly how it worked, but I remember hearing that they just scaled up this same algorithm. And what's neat about this is in chess, right, it's symbolic. But did we pass it? Yes, we did. Here we are. So in chess, it's symbolic. So you can say, and there's not that many possible moves. I mean, there's a lot, but a computer can kind of represent a lot of them. Whereas Go, what makes it so hard is there's so many possible game states, the computer can't begin to enumerate them or say, if I do this person's going to do that, and then I can do this, and they can do that all the way down, which is how we do chess. Go, you need to use more of a visual perception, kind of an abstraction of the space, and this is what allowed them to do that. So yeah, it was kind of like a pattern recognition approach as opposed to a purely symbolic approach with chess. But I'm not totally sure how they did it. Yeah, sure, yeah.
So what's the state of the art in mimicking or replicating a neural network given input-output pairs?
Yeah, so there's been some work on, you can take this trained neural network and train like a little brother to do the same thing and have it be smaller. That's about all I know, though. Yeah, but yeah, there's some neat stuff with that. And then you end up with a smaller network that does the same thing as a bigger network but uses less resources. Yeah, yes?
What opportunities in the Austin area for training other than self-study or UT on neural networks, deep learning?
I don't know. Yeah, I mean, I give a tutorial every now and then, but I don't know. I'm sure there are others, but I don't know.
Other meetup groups.
Yeah, there probably are. I don't know if they focus on like taking you step by step, but yeah.
At some level, some of them
Oh, okay.
can do that. There are wealth of meetup groups in the area.
Oh, cool.
In AI.
Oh, cool. Yes.
To what extent with your grammar are you programming in context? Because in some cases, a word might mean 20 different things.
Yeah, so it uses context of the other words around it. And you can take that even further, and we haven't done this yet, but it's a straightforward implementation. You can first get a vector for the whole document and use that as additional context. So you can know what kind of document it is and what they're talking about. So right now it uses the words around it, all of the words in the sentence, but you could even expand that out. In fact, you could even, because it learns instead of having to have everything written in, each of us could have our own personal grammar checker based on the text that it's learned from what we've written. Mm-hmm. Yes?
Really, I already answered my question.
This is sort of a clumsy social/business question, not so much human. I encounter quite a few people that think that machine learning AI is more of a sort of a black box that you can staple onto something and get a magical answer. Now with deep grammar, I'm sure you've probably encountered that a little bit. Like, why doesn't Grammarly just do the same thing you do, except for they'll throw some in. What's have you encountered that, and have you given a response?
Yeah, and it is kind of a black box in some degrees. And when deep grammar correctly corrects a sentence, I don't know how it did it. And when it makes mistakes, I can kind of try to look through and visualize certain things. But it is to some degree a black box. But maybe the bigger issue of your question is it's sometimes unclear where the limits of AI are. So when my daughter talks to Siri, she thinks she's talking to something. But it's clear to me that Siri doesn't understand, right? And it'll be fascinating as these chatbots get smarter and smarter. Do we start to get confused on what they really understand or what they're just mimicking? And we don't even know what the word understand means, actually. But, we take it to mean, do you have a broader context for what you're saying? And could you predict novel outcomes? But, there's no concrete definition of that. So, yeah, it's really easy to just get confused on what AI can do and what it can't and think it can do everything or nothing. And it's just, and there's really, like we're talking with self-driving cars, there's no guarantee. It's we just try things out and see if they work. Yes?
Just way out there, what do you think would be the characteristics of a quantum computer that can implement neural networks?
I don't know anything about quantum computers. I know that quantum computers can have represent all states at the same time, and that's where they get their power, and then they collapse. That's the beginning and end, though. That's all I know. So. Yeah, and I've heard smart people say that, yeah, this is the thing. It's, all this is going to be not important. And then I've heard other smart people say, no, they're inherently limited. I just don't know. And I don't think we'll know until we actually see them. Yes?
Well, I have a question about the blue cup problem in robotics that you had, and that it was difficult to make it understand other contexts, like if you let go of it, it will fall. Make a noise, and it will, other things will happen. Well, a lot of those things that can happen are actually described by physics, right? If it knew about gravity, then it would know that the cup would fall. And if it knew about friction, it would know that it would go along with the table if you pulled it. So, and those are relatively simple sort of mechanics, physics problems. And I'm wondering if that has been put into sort of the context of the neural net so that the actual robot doesn't have to actually experience all these things, meaning it doesn't have to have ears to hear something. Mm-hmm. It doesn't have to have a sense of touch to feel things. but it can learn mathematically that these things will happen. And I'm just wondering, has that been done, or is somebody sort of...
That's precisely in the direction I want to move, is giving the robot a model, a physics model of the world. And so, you know, when it sees a cup drop, it doesn't have to see the cup drop 50,000 times before it figures out. It just goes, oh yeah, well of course, gravity says it should, and then it should make a noise when it makes contact with something if it has some velocity. That'll make sense, and it can learn a lot faster. That evidently has been surprisingly hard because it hasn't been done. But yeah, I think that's the way to go. Is we need to build an understanding of the world. In fact, I just wrote a blog post a month ago about that very topic. That we need to give it actual deep understanding of the physical world. And if it has that physical understanding, then it won't have to learn as much. It'll be like scaffolding for learning. Mm-hmm. Yeah.
Will that make them limitless?
Limitless?
By giving them a model of the world, they might be a little bit more limited. Say we now want to move this artificial agent to Mars. There's other gravity.
Oh yeah, definitely, yeah. And so there's this trade-off. So the more you build in, the more limited it's going to be. That's right. However, and it's the same with us. Like we're born with biases, and we can only see certain things, and like we can't see ultraviolet light, and we're limited in that way. And it's going to be the same with AI. No, that's a very good point. You want it to learn as much as possible, because then it has broader possible upside. Mm-hmm. Exactly. Mm-hmm. Yes.
Someone asked about the AI community here in Austin, and there's actually quite a bit going on in the realm of NLP.
Oh, great.
Louise Black and Lynn Bender's event that they produced 2 months ago over at the university, the Texas Data Day, about half of the content was on NLP.
Okay.
There is a huge conference coming to Austin September 28th and 29th called talkabout.ai.
Oh, great.
Very well produced and full of speakers from around the world in this realm of NLP.
Yeah, great. Yeah, and there is I spoke at Data Day, and then there's also an NLP Day coming up with this Geek Austin, and I'll be speaking there, I think, on a different topic, NLP. So there's definitely that. Great point. And yeah, there are lots of conferences that come to town now and then as well. Mm-hmm. Well, great. Any other questions? Thank you.